So guys, that was all about decision trees. Now let's look at our next classification algorithm, which is random forest. Now, first of all, what is a random forest? Random forest basically builds multiple decision trees and glues them together to get a more accurate and stable prediction. Now, if we already have decision trees and random forest is nothing but a collection of decision trees, why do we have to use random forest when we already have decision trees? There are three main reasons why random forest is used. Now, even though decision trees are convenient and easily implemented, they are not as accurate as random forests. Okay, decision trees work very effectively with the training data, but they're not flexible when it comes to classifying a new sample, right? Now, this happens because of something known as overfitting. Now, overfitting is a problem that is seen with decision trees. Okay, it's something that commonly occurs when you use decision trees. Now, overfitting occurs when a model studies the training data to such an extent that it negatively influences the performance of the model on the new data. All right. Now, this means that the disturbance in the training data is recorded and it is learned as concepts by the model. If there's any disturbance or any sort of noise in the training data or any error in the training data, that is also studied by the model. The problem here is that these concepts do not apply to the testing data and it negatively impacts the model's ability to classify new data. So to sum it up, overfitting occurs whenever your model learns the training data along with all the disturbance in the training data. So it's basically memorize the training data, and whenever new data will be given to your model, it will not predict the outcome very accurately. Now, this is a problem seen in decision trees. Okay. But in random forest, there's something known as bagging. Now, the basic idea behind bagging is to reduce the variations in the predictions by combining the result of multiple decision trees on different samples of the data set. So, your data set will be divided into different samples, and you'll be building a decision tree on each of these samples. This way, each decision tree will be studying one subset of your data. So this way overfitting will get reduced because one decision tree is not studying the entire data set, right? Now let's focus on the random forest. Now in order to understand random forest, we'll look at a small example. Okay, consider this data set. In this data, we have four predictor variables. We have blood flow, blocked arteries, chest pain, and weight. Now these variables are used to predict whether or not a person has a heart disease. So we're going to use this data set to create a random forest that predicts if a person has a heart disease or not. Now, the first step in creating a random forest is that you create a bootstrapped data set. Now, in bootstrapping, all you have to do is you have to randomly select samples from your original data set. Okay, and a point to note is that you can select the same sample more than once. All right. So if you look at the original data set, we have abnormal, normal, normal, and abnormal, right? Look at the blood flow section. Now here I've randomly selected samples, normal, abnormal, and I've selected one sample twice. All right. You can do this in a bootstrap data set. Now all I did here is I created a bootstrap data set. Bootstrapping is nothing but an estimation method used to make predictions on a data by resampling the data, right? This is a bootstrap data set. Now, even though this seems very simple, in real world problems, you'll never get such a small data set. Okay, so bootstrapping is actually a little more complex than this. Usually, in real world problems, you have a huge data set, and bootstrapping that data set is actually a pretty complex problem. Now, here, because I'm making you understand how random forest works, so that's why I've considered a small data set. Now, you're going to use the bootstrap data set that you created, and you're going to build decision trees from it. Now, one more thing to note in random forest is you will not be using your entire data set. Okay, so you'll only be using few of the variables at each node. So for example, we'll only consider two variables at each step. So if we begin at the root node, here we will randomly select two variables as candidates for the root node. Okay, let's say that we selected blood flow and blocked arteries. Right, out of these two variables, we have to select the variable that best separates the sample. Okay, so for the sake of this example, let's say that blocked arteries is a most significant predictor, and that's why we'll assign it to the root node. Now, our next step is to repeat the same process for each of these upcoming branch nodes. Here we'll again select two variables at random as candidates for each of these branch nodes, and then choose a variable that best separates the samples. right? So let me just repeat this entire process. So you know that you start creating a decision tree by selecting the root node. In random forest, you'll randomly select a couple of variables for each node, and then you'll calculate which variable best splits the data at that node. So for each node, we'll randomly select two or three variables, and out of those two, three variables, we'll see which variable best separates the data. Okay, so at each node, we'll be calculating information gain and entropy. Basically, that's what I mean. At every node, you'll calculate information gain and entropy of two or three variables, and you'll see which variable has the highest information gain, and you'll keep descending downwards. That's how you create a decision tree. So we just created our first decision tree. Now what you do is you'll go back to step one and you'll repeat the entire process. So each decision tree will predict the output class based on the predictor variables that you have assigned to each decision tree. Now let's say for this decision tree, you have assigned blood flow. Here we have blocked arteries at the root node. Here we might have blood flow at the root node, and so on. So your output will depend on which predictor variable is at the root node, right? So each decision tree will predict the output class based on the predictor variable that you assigned in that tree. All right. Now, what you do is you'll go back to step one, you'll create a new bootstrap data set, and then again, you'll build a new decision tree. And for that decision tree, you'll consider only a subset of variables and you'll choose the best predictor variable by calculating the information gain, right? So you'll keep repeating this process. So you just keep repeating step two and step one. Okay, and you'll keep creating multiple decision trees. Okay, so having a variety of decision trees in a random forest is what makes it more effective than an individual decision tree, right? So instead of having an individual decision tree which is created using all the features, you can build a random forest that uses multiple decision trees, wherein each decision tree has a random set of predictor variables. Now, step number four is predicting the outcome of a new data point. So now that you've created a random forest, let's see how it can be used to predict whether a new patient has a heart disease or not. Okay, now this diagram basically has the data about the new patient. Okay, this is the data about the new patient. He doesn't have blocked arteries, he has chest pain, and his weight is around 185 kgs. Now, all you have to do is you have to run this data down each of the decision trees that you have made. So, the first decision tree shows that yes, this person has heart disease. Similarly, you'll run the information of this new patient through every decision tree that you created. Then, depending on how many votes you get for yes and no, you will classify that patient as either having heart disease or not. All you have to do is you have to run the information of the new patient through all the decision trees that you created in the previous step, and the final output is based on the number of votes each of the class is getting. Okay, let's say that three decision trees said that yes, the patient has heart disease, and one decision tree said that no, it doesn't have. So this means you will obviously classify the patient as having a heart disease because three of them voted for yes, right? It's based on majority. All right. So, guys, I hope the concept behind random forest is understandable. Now, the next step is you will evaluate the efficiency of the model. Now, earlier when we created the bootstrap data set, we left out one entry sample, right? This is the entry sample we left out because we repeated one sample twice. If you all remember in the bootstrap data set, here we repeated an entry twice and we missed out on one of the entries, right? We missed out on one of the entries. So what we're going to do is, so for evaluating the model, we'll be using the data entry that we missed out on. Okay. Now in a real world problem, about one third of the original data set is not included in the bootstrap data set, right? Because there's a huge amount of data in a real world problem. So one third of the original data set is not included in the bootstrap data set. So guys, the sample data set which is not there in your bootstrap data set is known as out of bag data set. Okay, so basically this is our out of bag data set. Now the out of bag data set is used to check the accuracy of the model. Now because the model was not created by using the out of bag data set, it will give us a good understanding of whether the model is effective or not. Now the out of bag data set is nothing but your testing data set, right? Remember in machine learning, there's training and testing data set. So your out of bag data set is nothing but your testing data set. This is used to evaluate the efficiency of your model. So eventually you can measure the accuracy of a random forest by the proportion of out of bag samples that are correctly classified, right? Because the out of bag data set is used to evaluate the efficiency of your model. So you can calculate the accuracy by understanding how many samples was this out of bag data set correctly able to classify. So guys, that was an explanation about how random forest works. To give you an overview, let me just run you through all the steps that we took. So basically, this was our data set, and all we have to do is we have to predict whether a patient has heart disease or not. So our first step was to create a bootstrap data set. A bootstrap data set is nothing but randomly selected observations from your original data set, and you can also have duplicate values in your bootstrap data set. Okay. The next step is you're going to create a decision tree by considering a random set of predictor variables for each decision tree. Okay. So the third step is you'll go back to step one, create a bootstrap data set, again create a decision tree. So this iteration is performed hundreds of times until you have multiple decision trees, right? Now that you've created a random forest, you'll use this random forest to predict the outcome. So if you're given a new data point and you have to classify it into one of the two classes, you'll just run this new information through all the decision trees. And you'll just take the majority of the output that you're getting from the decision trees as your outcome. Now, in order to evaluate the efficiency of the model, you'll use the out of the bag sample data set, right? Now, the out of bag sample is basically the sample that was not included in your bootstrap data set. But this sample is coming from your original data set, guys. This is not something that you randomly create. All right. This data set was there in your original data set, but it was just not mentioned in your bootstrap data set, right? So you'll use your out of bag sample in order to calculate the accuracy of your random forest, right? So the proportion of out of bag samples that are correctly classified will give you the accuracy of your model.